A Monte Carlo analysis randomly varies every parameter in your circuit that has a tolerance assigned to it and then plots a distribution of the results. For this circuit, we'd like to use a Monte Carlo analysis to calculate the electrical yield for obtaining a low-pass, 3 dB bandwidth of a minimum of 181.5 MHz, and also the yield of having a minimum gain of 17 dB. The Monte Carlo analysis will vary the parameters of all the components in the design that have tolerances assigned to them. We can view and edit the tolerances in our design using the assigned tolerance form, which we can access by selecting PSpice Advanced Analysis, Assign Tolerance from the Capture Text menu. A netlist is generated, and we can assign both global and instance tolerances. If we expand the global list, we can see that we can set global tolerances for our resistors, inductors, capacitors, voltage sources and current sources. When we select R for our resistors, we can see that those have a positive and negative tolerance set to 10%. During our Monte Carlo analysis, our resistor values will be varied from their minimum tolerance to their maximum tolerance, randomly using either a flat distribution or a Gaussian distribution. For our resistors, we'll select a Gaussian distribution. We could also see that our capacitors have a positive and negative tolerance of 10% as well. For specific, discrete components, you can override the global tolerance values using the instance list as well. If we select R3 in our instance list, we can see that our R3 resistor has a positive and negative tolerance of 20%, which will override our global value of 10%, and that it will also use a Gaussian distribution. Our global distributions will be stored in the SPICE initialization file and will be applied to all of our advanced analysis projects. Our instance tolerances are stored as properties on our schematic and will only apply to this specific project. To measure the low-pass 3 dB bandwidth and the gain, we've created a simulation profile called AC that sweeps the frequency of our source from 1 MHz to 600 MHz logarithmically with 100 points per decade. This AC simulation profile is our active profile. So we'll select the Start Simulation icon to begin our standard PSpice simulation. After the simulation, the trace window is displayed. We'll view the voltage at our output in decibels by selecting Trace, Add Trace to open the Add Traces form. We'll select the dB function in the Functions and Macros section of the Add Trace form and then insert the voltage at our output. Since we named the output signal out, we should have an entry VOTE that we can select and then view the voltage at our output in decibels. We also need to add a measurement for our 3 dB low-pass cutoff frequency. So we'll select Trace, Evaluate Measurement from the Trace window, and in the Evaluate Measurement form we'll select the cutoff low-pass 3 dB measurement and we'll insert the voltage of our output net. Our measurement is added to our measurement results spreadsheet, and our 3 dB cutoff frequency is about 186 MHz when all the components in the design are set to their nominal values. To measure the DC gain, we'll again select Trace, Evaluate Measurement from the Trace text menu and then select the max function. Inside of the max function, we'd like to measure the voltage at our output signal in decibels. So we'll set our measurement or functions field to analog operations and select the dB function, and then over in the simulation output variables section of the evaluate measurement form we'll scroll down and select the voltage of our output net. The measurement is added to our measurement results spreadsheet, and we see that the DC gain of our circuit, using nominal values for all the components, is about 18. We can now import our measurements into the Monte Carlo analysis application and run our Monte Carlo analysis. We'll go back to our capture window and select PSpice Advanced Analysis, Monte Carlo from the Capture Text menu. The Advanced Analysis user interface is displayed and we can click in the Statistical Information spreadsheet to import the measurements that we created in PSpice. The Import Measurements form displays the two measurements that we created in PSpice and we can select them both using the Control key and our left mouse button. We select Edit, Profile Settings to set the settings for our Monte Carlo analysis. We'll simulate our circuit 1000 times and each time, the parameters of our components that have tolerances will be randomly varied. The pseudo-random number generator will begin with the same seed number each time we run a Monte Carlo analysis, giving us the same results every time we run the simulation. We can enter a different random number seed in the Monte Carlo Profile Settings window. We'll select OK in our profile settings and select the Start icon from the Advanced Analysis user interface. After all the simulations are finished, the results are displayed in the Advanced Analysis application. The results are first displayed as a probability density function and we can switch between the probability density function and the cumulative density function by holding down the right mouse button on the graph and toggling the MC graph option in the context-sensitive pull-down menu. The cumulative distribution graph shows the cutoff low-pass 3 dB frequency along the x-axis for our measurement and the y-axis shows the number of runs that met a particular 3 dB cutoff frequency. To find the yield of the number of runs that are met, our low-pass 3 dB frequency of 181.5 MHz, we can select the minimum marker with our left mouse button to select it and then select 181 MHz on our graph. We'll then select our maximum marker and place it at a location that includes all 1000 of our runs. The statistical information spreadsheet indicates that 63.5% of our runs met our goal of a 3 dB cutoff frequency of 181.5 MHz. Similarly, we could display our gain measurement in the statistical information spreadsheet and place our minimum marker at our goal of 17 and our maximum marker somewhere that includes all 1000 of our runs, and we see that 99% of our runs meet our gain requirement of 17 dB. The Monte Carlo analysis data can also be viewed as a portability density function by holding down the right mouse button on the graph and toggling the MC graph option in the pull-down menu. For our gain, the x-axis shows the gain, while the y-axis shows the number of runs that fit into a gain range. We can hover a cursor over one of the bars on the graph to view the range. So for a gain range of 18.2 to 18.5, 219 of our runs out of 1000 were in that range. If we move out cursor over towards the right, we see that for the range of a gain of 19.13 to 19.44, 36 of our 1000 runs were in that range. We edit the number of bins on our bar graph by selecting Edit, Profile Settings and changing the number of bins from 10 to, for instance, 25, so we now have more bars on our bar graph. The Monte Carlo analysis randomly varied every parameter in our circuit that had a tolerance assigned to it and plotted the distributions to allow us to analyze our circuit.